Now, once you've installed your STM32 CUBEIDE, it's time to start using it. So I will be showing you, I'll be giving an introduction of the CUBEIDE on Linux. Specifically, I'm using Linux Mint 20.3, but those of you on Windows can easily follow. So let us first open CUBEIDE. So I have opened this ID a couple of times before, so there'll be certain settings that I might not be needed to do, which you would have to do. First thing is setting up the workspace. So this is where my workspace is. Workspace is where your complete code and all your artifacts are going to reside. So this is it. It prompted for this workspace to me, and I've just left it as it is. I've not changed it, and I could also tick this and say use this as default and do not ask again, but I've not done it. And then click on launch. First time when you launch your CUBEIDE, now we launched the CUBEIDE previously also when we did the install, but when you launch the CUBEIDE, this is what you're going to get. It is going to open on the Information Center tab. So now you have start new STM32 project, start new project from STM32 CubeMX file, import project, import STM32 cube example, and so on. Now we will not be using anything here, but there are a few interesting links that you can actually explore. One is STM32 CUBEIDE resource portal. Okay, so if you click on that, it takes you to a STM32 web page, and it gives you an introduction to CUBEIDE, and it has some documentation, training videos, and other resources including example projects. So it has a lot of information on CUBEIDE. So if you want to go through them, feel free to navigate this. Okay, it gives you, talks about the software development kit, talks about the CUBEIDE tutorials, and so on and so forth. So you have many tutorials to view here. But as far as we are concerned, okay, here you have the STM32 CubeMX tool, Cube Monitor, CubeMon RF, Cube Programmer. Cube Programmer is what we have already installed. Now we are not going to use anything from this particular page. Okay, so you can close this off. When you close this, this is what you are greeted with. This is your STM32 CubeIDE page. Now, this is the name of the workspace. This is your menu. These are your tools actually. Okay. This is going to be a project explorer, and you will have different views. So since this is Eclipse, and ST has wrapped its own tools and packaged its own tools along with Eclipse, the IDE looks very similar to the native Eclipse IDE. It is Eclipse, in fact. Okay. So since our course is a bare metal course on STM32 Cortex-M4, we will not be using any of the STM32 tools to create our project. Instead, we are going to, since we have our Makefiles and linkers ready, so in our case, we have the code, the Makefile and the linker script ready, and we will be working on Makefile projects throughout this course. So we will not touch any of this. Now, working on Makefile projects has an advantage of you compiling or building that project as a standalone application in a terminal. That is, you can build that particular project using the make command through a terminal and then flash the binary file on the board even without using the STM32 CUBEIDE. Or you can open that same Makefile project in CUBEIDE and you can use the editor and you can start developing on your project. Okay, so you can there are multiple ways by which you can approach your particular development environment. So we will do both, especially in the Makefile linker segment. We will see how we can also write a binary using the STM32 programmer. So let's get started here. So we will create a new Makefile project. So just click on this. You can also the project from file new, and then you can create it from here as well. That is file new and Makefile project with existing code. So either way. So click here, give it a project name. So since we are in the first chapter, we will say basics. Okay. And then existing code location. So we will browse to our existing code location. So we are in the folder which has the code, and we go to that folder, the root of that folder, basic code, and then we say open. When you come here, you can keep it as C and C++, but the compiler you choose is MCU ARM GCC. So don't choose anything else, choose MCU ARM GCC and click on finish. When you click on finish, the project gets added to CUBEIDE. Whatever source you see here is being taken from this folder. So even though the workspace is somewhere else, it is going to work on these files, and any changes you make in the IDE will reflect on these files. So now, of course, this is the editor area. So let's have a look at the Makefile first. So if this is your Makefile, we'll see what are the files that are being used for this particular application. We have startup gcc.c, core initialization STM32F411xc.c, and memory access methods.c. Not to worry, we will have an exhaustive session on how to write Makefiles and linkers later. So do not worry, and there's no need to get overwhelmed seeing the Makefile here. We have this is the main C file that we have here. So let's check out the memory access methods.c file, and this is the file here. Okay, so this is the C file here that is where you are going to write your code. Suppose not only this, there are a few other files also. So the hierarchy here is this is your root, that is the demo code that you saw, which I added, and then you have an include folder which contains a memory map STM32F411xc.h header file. Then there's a source directory which has your core initialization routines, that is and drivers, and then it has got the startup file, that is the startup gcc.c, and then the other application files are here. In our case, it is only one application file, that is memory access methods.c. So this is the setup right now. So for you to start anything on this, you could choose to. So we have the menu here, of which this is the project menu where you can close this project, you can build this project. Okay, you have the different build configurations, will not touch that. And we can clean this project. So we will be using build all and clean mostly. Okay? And when we come to the chapter on make, we will talk more about this, but your Makefile, whatever you have, must have the target all and target clean. And that is how the CUBEIDE recognizes this Makefile, and it also looks for the .out file here. It checks for the name of the .out file and it adds it to the .out file that it is going to. So the .out file is prerequisites.out. So let us see what. Let us go to the debug configuration. Okay? So this is when you click on this, click on the down arrow next to the bug here, debug basics. You can go to the debug configurations, and when you go to the debug configurations, you can just STM32 C++ application, and when you click here, nothing happens. So just close this, and with this highlighted, try to start a debug session and see what happens. So when you start a debug session, since no debug configuration was created, it will edit a launch configuration property. So you can do basics default. It could be the name of your configuration. Okay, project name is basics, of course, and see, it has makes CUBEIDE is intelligent enough. The .out file is prerequisites.out. So it looks for the .out extension and it adds this automatically. You can change the name here. If you change the name here in the Makefile, you have to accordingly change the name of the .out file. Okay? That's all you need to do. Nothing more to be done here. So the configuration is pretty easy. You don't need to go into any kind of plugins, or you don't need to. There is no involved setup here because the Makefile and the linker takes care of a lot of settings. Just do an OK. When you do an OK, this will start building, and if everything goes fine, the debugging session is going to start. So it downloads the code and the debugging session starts. Now, as you can see, the control is here. So we can single step, or we can run the code, and we can do a lot of things. Now, before let's close the debugging session now. So there is a few more things that so you can, like we were saying, project, you can clean the project up. Clean means whatever is the clean rule that we have in the Makefile. That is, here it says remove all .o, .bin and .out files from the project folder. So that is what it has done now. So it has removed everything. So now when you do a project build all again, it builds the project, but it doesn't flash it on the board because it just builds the file. So it's make all, and it's created the build. Okay. Now this bin file does not go to the board, and we have talked about it extensively in the Makefile linker chapter. But then .out file, the prerequisites.out file that you saw, which we have mentioned in the Makefile, is the one which is used to create the binary file. So it is a prerequisites.bin or some binary file the CUBEIDE creates internally. So this bin is, even though it is created, it is not used by CUBEIDE. Now in the run, you could run this. So when you run it, it actually flashes the code on the board and it allows the code to run. Okay. It does not debug the code. So you don't get into a debug session. Your code just runs. There are a few more debug configurations that you need to be aware of. For example, if you click on debug configurations, now a new configuration has been created, basics default, because it asked for that, if you remember. So the project is basics, and the .out file, whatever was put there, has come here. Go to the debugger tab. This is the debugger you are going to use, ST-Link GDB server. Okay. So this is the debug probe that you are using. So this is the debug probe that you have on the discovery board, that is on your STM32F411 board. So we are using the onboard debugger, and the interface is SWD, so that is serial wire debug. Okay. So this is your configuration, and you don't need to do anything yet, but then you need to know, if you see the drop down, there's a Segger J-Link. If you're using a Segger J-Link debugger, or you could use a ST-Link OpenOCD debugger also. We are not using OpenOCD. We'll straight away use the ST-Link GDB server. Okay. So this is the configuration. That is all you need to worry about in our case. So it's pretty simple. It's pretty straightforward, and I have tried to keep it as simple as possible so that we can focus on our main goal, and that is to understand the Cortex M4 architecture and setting up the Cortex M4 and beginning to code on it. So having said all that, so we have some views here: problems, tasks, console, where your console messages will come out when you are whatever, if there are any errors, and if you are whatever make command that the CUBEIDE issues from following the Makefile, everything comes here. Properties and disassembly. Now this is the Eclipse actually, because this is Eclipse working under the hood. Eclipse works with the concept of perspectives. Now a perspective is a collection of views. So this is one view. So this is your editor. This is a console view. This is your project explorer. So a collection of these views is one perspective. Similarly, you can have a debug perspective, as you can see here, but since we are not debugging, you'll not see anything here, but this is called the debug perspective. So terminated exit. So there's no debug here, but then you have a debug pane, and then you have variable views, and then breakpoint views, and expressions, and register views, disassembly view, and then live expressions, and so on and so forth. Registers, variables we just saw. Okay. The moment we put this on debug, that is, put this code on debug, all these views are going to get filled up with relevant information. So let us put this on debug once again and see what happens. So now you can see the debug tab has got relevant information. It is main at access methods. It shows you the at what address it is starting, and it gives information about the state of the debug that we are in right now. Okay. So this is the debug perspective, and the debug perspective is and like I said, these views are going to get populated with relevant information, relevant data. Now there are a lot of new tabs that have got added. So you have console, and then problems, executables, memory browser, memory, debugger console, variables, build analyzer, SWV trace. And this one was added by me, but then it comes up to build analyzer. Now what can you do with this? So you are in debug view. So this is your code, okay, and you can nevertheless go into the project explorer and open up other files actually. So let's close this one. So you can open up this C file, which is a core initialization C file comprising of drivers and other initialization code, and this is the main that we have, and our control is currently here. So debugger is generally we generally single step, we halt the program at every step of the code, and then we inspect the code, and for bugs, or for understanding the code, or for any other purpose. So since we are in the debugger state, let us see what are the possibilities that we have here. So straight away we can, so if you come here, if you look at these tools, you have a step into, step over, disconnect, terminate, resume, that's continue, that's run, and this one terminates and relaunches the debugger, and this is reset. So it resets the program counter and it comes back here. Okay, and this is the debugger button and this is the run button and so on. So now what can you, so you can step into would mean, if you are, this is a function call. If you do a step into, you're going to go into that function. If you do a step over, you're going to come to the next line in the same file. Okay, so let's do a step over for now. So if you do a step over, the code comes here, and then suppose you do and the shortcut for step over is again F6. So if you press F6 also, it goes to the next line. Okay, so it steps. So the code is getting executed and then it is getting trapped in the next line. It is not executing continuously. Okay, that is the job of the debugger, to stop the code and inspect the different registers and inspect the microcontroller for either problems or for other purposes. So now we saw two ways of doing a single step. That is, you can step into, or you can step over. You can click on this button, or you can press F6 as it shows here, the tooltip. There is another way of doing it, that is the GDB debugger prompt. So you can also interact with the program using the GDB debugger. So for example, if you press S here, it means step. Okay, and this is the standard debugger that you have. So this is the ARM GNU debugger. So anything that you can do through the UI, you can do using this debugger. Okay, for example, you can step, if you press C, it will continue, and so on. If you want to set a breakpoint, that is, you run the program and you want it to halt at some particular line. Okay, for example, this one, line number 72. So you want it to halt at this line. That is, allow it to run freely, but whenever it comes here, it should stop. So you could do this. You could press F8. You could press this button to resume, or you could come to GDB and say C, that is continue. And you will see that the control has come here and gotten stuck at this point because we set a breakpoint. You can again double click on the breakpoint to get rid of it. So now the breakpoint is not there. Okay, and as the program is moving through, as the control is moving through the program, you would see that these values are changing. That is the variables. Now we have not added any variables. These variables have got added automatically. So clear bits, bit pattern, these variables are changing. So if you want to inspect the variables, you can inspect them here, and that is what we need to do. We set a breakpoint and we removed it. So expression value 1. So this is a watch. Now these are your expressions. Okay, what are the different expressions that you have? For example, ampersand TBS, ampersand DST, all the expressions that you have in the program, test3 and so on, general purpose registers. More than expressions, we will have to, this is a very important view, which is the register view. So here it gives you a view of all the registers of the ARM processor that you have, that is R0, R1, R2, R3, everything. Okay. Stack pointer, link register, program counter, XPSR, and it gives you a view of the floating point registers also. So you can inspect all your registers from here, but it does not give you a view of your peripheral registers, that is the configuration registers, RCC, and so on and so forth. So for all of that, you have to go into memory addresses and then inspect them. Next view is the disassembly view. Very important. Disassembly view is where you, for this C code that we wrote, there was an underline assembly code that was written. This is that view. So it actually shows you that for cystic load based particular line of code, what is the assembly code that has been written here. So there are a lot of LDR instructions, ORRS and STR and so on. So these are the assembly instructions that are corresponding to this particular line of code. So as you can see, it's one line of code, but the assembler has to work hard behind the scenes to create the assembly code to represent that particular line of code. Okay, and this is extremely important. So you will have to sometimes inspect what is really happening in assembly if you see a bug, and maybe there is something going wrong here, maybe some memory access issues or any problems for that matter. So a disassembly view is extremely important, even though here the assembly is completely created by assembly code is completely created by the compiler, and then the assembler converts this into machine code. But still, it is important to know about what is really going on in assembly. Not always, but sometimes. And then you have SFR. So all of this is not that important. So disassembly, register views, and variables are one of the most important views. And you have the GDB here. You could set breakpoints using the GDB, but sometimes I have seen the CUBEIDE gets confused when you set a breakpoint through here and here. Whenever you have a problem like that, that is, you have some breakpoints, sometimes it will happen that it will complain about some breakpoints which it is not able to account for. In such cases, you have to clear all breakpoints. Okay, so create a few breakpoints here. So we have 2 breakpoints, and suppose you've forgotten where you have set your breakpoints. One thing is, you can actually investigate here, and you can see what are the what you have set here. For example, you have set a breakpoint in line 67, you have set a breakpoint in line 74, you have set a watch on value 1 on here. Okay, so all of that you can inspect from this pane, that is the breakpoints pane. So that is another thing. Now coming down, you have the memory browser. The memory browser is where you can view the memory of the controller in real time. So 0x, let us view the code memory. So 8000000. So when you view the code memory, you will see that this is your exception vector table, and it goes down. Let us bring this up a bit. This goes down all the way to here. And this is from where your actual thumb instructions start. Okay, so we'll see all that later. But if you want to, you will need to inspect the memory in many instances. So this is your flash basically. So if you say you want to view the RAM area, so RAM area say starts from 2000000. So this is your RAM area. Okay, this is your RAM. This is your data, initialized data area, and then you have your PSS area, and then you have your stack. Everything is here. Okay, so if you want to inspect your RAM, suppose you want to inspect your peripherals like 0x40020000. So this is actually your general purpose input output register. Okay, that is GPIOA mode setting register. So this is your GPIOA mode setting register. Okay, so we'll see all this later, but I'm just telling you. And it is possible also to alter the values of your when you come to RAM. Suppose you come here, you can actually alter the value here. So suppose you can just alter the value like this on the fly, and the value is actually going to be altered in the memory. Okay, so that is also something that you can do. If you press enter, this particular value gets altered. So that is also going to be necessary in certain cases where you check something. Okay, and you want to directly access that particular memory region and make some changes to it without writing code, you can do that. Next is memory. You can add similar to memory browser. Okay, so there's something else that I need to show you in the memory browser. There's an big and little Indian view. So the as you know, Cortex M4 is little Indian architecture. So you can view whatever you are viewing is not according to the order of the bytes that you have in the address. Little Indian, you're seeing it like this for your convenience, but it is in the opposite direction actually. So it is 2042000020, something like that. So it goes like this. Okay, so the individual bytes go in the opposite direction. This depiction, this representation that you're seeing is only for your convenience. That is how the IDE is showing it to you. If you change it to big endian, then you'll see that. If you change this view to big endian, make it big, you see that everything changes and goes in the other way around. Okay, so it looks different because now the order of the bytes have changed. Let's make it little endian, and let's see 80000x8. Sorry, 10 less. So this is the view. So if you make it big endian again, as you can see, the whole thing reverses actually. Okay, so it depends on your convenience. This is the actual byte representation here, 14040020. This is how the bytes are actually organized. But then if you want for your convenience, if you make it little endian, this is how you view it. Next tab is the memory tab, where you can add memory addresses. For example, I'll add 0x. Oh, I'm sorry. Say you add 0x, same memory, 800000. Okay, and then if you do OK, that particular memory gets added, and here it shows the way we saw the big endian view. See, from bit 0 to 3, the representation is the way it should be. For example, 14040020. So this is sometimes very important. You could view your stack and everything through the memory browser. We'll do that. We'll see that. Okay, and then you have and you can add different memory locations here, and you could view them for later. So as long as you keep the project, in the sense you don't delete the project, you can close your IDE. If you come back, all of those values are going to be saved for you. And the debugger, suppose you want to view the stack pointer. Okay, so x, and let's say 10x. I don't know the size of the stack. Okay, but anyway, so see, this is so this is going to be your stack contents. So we'll talk about the stack pointer and stack contents in great detail later. But see, this is how you can view a lot of different memory locations using the GDB debugger also. So you can issue commands to the terminal here, and you can view the stack and view different. You can view the registers, and you can view a lot of things here. Okay, standard GDB and ARM GDB commands. We'll not go deep into this because learning ARM GDB is not the intention of this particular course. But then we will be using basic GDB commands here and there. So we'll have a fair understanding of GDB by the end of the course. Basic understanding. Okay, then you have the variables, which is the same as this one. And then the build analyzer doesn't show anything. Okay, so this is in brief what you can see, and you single step through, and you set a breakpoints. For example, you set a breakpoint in core initialization in some routine where you want the control, where you know that the control will pass through, and the control you want the control to stop. For example, just put a breakpoint here, and then allow the code to run freely, and you'll see that it has gotten stuck there. And then you can investigate the disassembly view and what the state of the registers are, and so on and so forth. Then we will be repeatedly using the IDE over and over again. So you, and definitely you will follow along. So you will become comfortable with this as we proceed. So that should not be a problem. So that's all. And we are, as I stated, we are not using the complete, all the capabilities of this, all the features of the CubeIDE. We are only using it as just for debugging purposes. And since we have the Makefile and linker written, and we are aware of the particular processor architecture we are dealing with, we are going the hard way. So we are not, you can say that we are not driving an automatic, we are driving a manual transmission vehicle. So that is how the course is going to go for you, and it is important for you to understand it this way. If you understand the GNU GDB tools properly, you understand Makefiles and linker, when you go on over to simpler IDEs which do a lot of things in the background for you as well, still you will actually know what is going on, and that is very important. So let's stop the debug session and let's go to the project view, say run. So here you have skip all breakpoints or remove all breakpoints. So now as you see, the remove all breakpoints has come. If you click on this, all your breakpoints are going to be removed, and your program you can start the program fresh. So it removes all breakpoints means even if you close the debugger and brought it back, the breakpoint information would have been remembered. Now we have removed everything. Okay. So this is in short how to start with the CubeIDE. So after this, let us also have a brief look at the STM32 programmer. That is, the job of the programmer is just to flash code on the board. That's all it does. It doesn't do anything else. But nevertheless, you might need it because in the Makefile linker we have used that programmer briefly. That is to flash some binary on the board. Let us just have a look at the programmer also. So closing this IDE now, and then opening the programmer, STM32 Cube programmer, and this one again uses the ST-Link only, and you can actually program through the UART and USB, but we are using the ST-Link debug probe only. That is the onboard debug that the discovery board has, and it has got memory and file editing. This is if you want to edit memory and things like that. So now this is in the disconnected state, and you can click on this button to connect it, and you can see that you immediately see the flash dump that we saw in the IDE, CubeIDE also. So this is what you can see, and you can edit. I think you can also edit the memory and do a few things here, but we don't want to do that. Our main concern here is this. That is, you can browse here, and this is your flasher basically, and start address is automatically put to 8 with 6 zeros. This is your start address. We say verify programming after flashing, and you could do a lot of operations on the flash memory, but generally we don't touch this. You can do a full chip erase also. It will just erase your flash on the board, or you can, this is your browse button. You go to the .bin or .elf, whatever file that you have, and you can click on the start programming button, and it will write your code onto the flash on the discovery board. This is what happens in the background with the CubeIDE also. Whenever you are actually pressing the debug button or pressing the run button, this is what happens in the backend. But this is the tool. This is a separate programmer tool which you can use to program. So say you compile something using the Makefile and using a make, and you have a linker and a binary file is created and you don't want to use the CUBEIDE, say, you could always use this STM32 programmer and you can directly program the binary on the board. And once you reset the board will start executing the code. So this is your programmer, and there are some other views here, option bytes, and it talks about your CPU, the whatever the CPU has, all the register views which we already saw. What is the system clock view, 84 megahertz, and so on and so forth. Okay, and then you have this we are not using secure programming or anything of that sort. So this is in brief what your STM32 programmer looks like. So going forward, we are actually going to go into basics of STM32 programming. We will learn about the basic C prerequisites that you need for embedded programming in this chapter, and then we'll continue from there.